Welcome to my science stream, or more of a video about my first science stream. The topic was finding extrasolar planets. Sadly, that stream got lost in the void. I forgot to save it. So to complete the collection of this series of streams about astrobiology, I'm gonna make this small video. Well, it's probably still an hour or so, but yeah, I'm gonna make this video to recap about the topic of finding extrasolar planets. First, we talk about why it's so hard to find extrasolar planets. So the problem is, of course, they're very dim. They're very dim objects. They're very hard to see because, not unlike stars, they're not shine on their own. They simply reflect the light that reaches them from the host star. Direct observation is because of this very difficult. Luckily, there's a solution to this problem, and that is indirect observation. Planets will influence their host stars, like bodies will influence each other. So even if it's just like a little bit or a tiny amount, planets do affect their host star, and because of that, it's possible for us to observe them indirectly via the host star. First property that can be changed by the presence of a planet is the luminosity. The luminosity, of course, does not change, which is the amount emitted by the star. What changes is the flux, the light that reaches us. The light that reaches us from the star is getting weaker the farther out we are from the star, or the planet is from the star. So we have the star here, and it basically has to illuminate this imaginary sphere around the star. So the smaller the radius is from this imaginary sphere, the smaller is the surface area the star has to illuminate. Now if we go further out, the radius of this imaginary sphere increases, and the surface area the star has to illuminate is much larger. Meaning the light has to distribute, the same amount of light has to distribute on the surface area, so the star is going to appear less bright. We have the planet here, and if the planet is farther out, less light will reach the planet and it will reflect less. So R is the radius, A is the surface area, and so the surface area increases, so we get less light. And from the amount of light that reaches the surface area, also only a small part is reaching the planet. Another property that is changing is motion. Two bodies are influencing each other, and we have the star, which is much larger than the planet, and therefore will have a larger influence on the planet. But even so, we have the planet here. The planet does influence the star a little bit, and that's a property we can observe. So the change in the light, or the amount of light that reaches us, and the change in the motion property. So observing these changes lets us conclude of the presence of an exoplanet. There are 5 main techniques we are going to talk about in this video. And they all rely on these parameters. The first one is the transit method. It's a very well-known method and a very successful one. It uses the luminosity as a parameter. The second one is the radial velocity method. It's basically also luminosity, but it's about the frequency of light that changes. The third one is the astrometry method, and also then the fourth one, direct imaging. Both of these methods rely on the motion parameter. The last one is the gravitational microlensing lensing method, and that also again depends on a change of light that reaches us. Okay, let's first talk about a bit what qualifies a planet to be a planet. Yeah, we know since Pluto that there's some kind of check marks. It's basically just a definition. So first point is it must orbit a stellar object, of course. So that's pretty easy, I guess. The second one is that it must have cleared its neighborhood. So it must be the only object in this orbit. The third one is that it mustn't exceed a certain mass limit. It's the mass of 13 Jupiter masses. The Jupiter mass is 1.8 times 10 to the power of 27 kilogram. If this mass limit is exceeded, then thermonuclear fusion is starting on of deuterium, so it doesn't qualify as a planet anymore, more like a star, a brown dwarf. The last point is it must be stable via self-gravity. So it must have reached hydrostatic equilibrium. Now if we have a star, which is also stable via self-gravity, we have all these layers and gravity forces pressing on the star, and then we have the gas pressure pushing back outside, so maintaining this equilibrium. So it's gonna be compressed to a compact shape of a sphere. And for planets, it's like internal pressure that has to withstand, so it has to have a sufficient amount of mass to sustain the body forces. So if all these 4 points are met, it's a planet. Pluto lost the status as a planet because it did not clear its neighborhood. So it's your goddamn own fault, Pluto. The transit method is the first method we're going to talk about. The parameter that changes here is of course the brightness of the star. We are measuring a decrease in brightness when the planet passes the star. Just like a solar eclipse, where we have less light from the sun reaching us when a planet is in front of it. So the flux here is the light that is reaching us, and the time we observe the system. So we have a sudden drop in brightness, which is the exact moment of a transit. So we have the star here, and there's the planet. The planet is orbiting the star, and eventually it will move in front of the star and taking away light. That's why we see this decrease in brightness. And then it repeats this pattern. So we will see the same decrease in brightness with every orbital period of the planet. The duration of the transit and the period does provide data about the distance of the planet from the star. Okay, we have the flux here and the time. Now as the planet moves around the star, we have a repeated decrease in brightness. So every time the planet orbits the star, again it will go in front of the star and remove some light, or like block some light. And the longer this period is, the farther away is the planet from the star, or the shorter is the orbital period, right? The slower, I mean, the planet is orbiting around the star. One problem is the observation time. We will need many years of observation of a system because it takes as long for a planet to orbit its star. So it's going to be easier to find planets closer to the star because it takes less time. Okay, so we have the star here. A star has a certain radius. And the transit duration is for the whole diameter. The transit duration is proportional to the distance to the star. It's also proportional to the stellar radius. Of course, if the star is larger, then it takes longer. And it's also proportional to the planet's radius. Because of this proportional behavior, we can conclude on the planet's mass and size, If we get a stellar mass and stellar radius from other sources like spectral analyzers, then we can conclude to the size of the planet. Because we know how big the star is and we see how much the planet then covers from the star. And if we know the mass of the star, then we can also conclude on the mass of the planet based on its orbital parameters seen by the light curves, or the change in light curves. The shape of the light curve depends also on its inclination. Then we also have to think about limb darkening. Now the inclination is of course a problem. Now we have here the scenario of a face-on view. Oh no, edge one, this is the edge one, so we see the sun, the star, and the planet is right in front of it. We can either have the edge on case, which we have here, so the orbit is right in front of the star. Now if we have face on, like the third one here, then we cannot see a change in brightness at all. Like mostly it's gonna be a mix of all of that. Stellar limb darkening means that the stellar disk is not evenly bright. So it's gonna be brighter in the center. And less bright on the edges. The number of planets detected by this method has increased steadily over the time. So it's a very popular method. We can also get clues about the planet's atmosphere, because the planet is in front of the star. So light from the star goes through the planet's atmosphere, and then we have a change in the light. So some light gets absorbed by the atmosphere of the planet, which then enables us to conclude of the chemical components of the atmosphere. So some will get strongly absorbed, or like some part of the wavelengths of the light from the star will get more absorbed, and other is just passing through. It can also conclude to rings around the star if the cover of the planet is not perfectly opaque. The radial velocity method is another indirect method that relies on us observing the change in radial velocity of a planet, of a star. So a star has a certain kind of radial velocity. It's the velocity to our line of sight. So if it moves away from us or towards us. And this kind of shift is what we observe. If we have two objects that orbit each other, they have a common center of gravity. So a planet is not really orbiting a star, it's more like the star and the planet orbiting a common center of gravity together. So we have the star here and the planet, and of course the star is way more massive as a planet, so the center of gravity will be close towards the star. Now if a planet orbits a star, we can see an offset in the position of the star because the star is moving around this center of gravity. Its shifting positions due to the planet influence. It seems like the star is wobbling. And this effect is causing a subtle change in the radial velocity, the velocity of the star towards our line of sight. So we have the star here, and the star is moving around this center of gravity. The planet will be here in this case, also moving around the star. we are, as an observer, this is us, this is Earth, we are observing the whole system from far away. And because it seems like the star is moving away from us in this case, we have a redshift. The light the star emits is getting redshifted. Because if a star moves away from us, the light waves leaving the star are stretched out. So if they move away from us, the light gets shifted towards the red end of the spectrum. Now if we have the other case, we have the center here, now the star moves towards here. It's still rotating, of course, around the center. And the planet is gonna be moved towards here. Of course, still orbiting the star. We as the observer, we are far away, and our positions towards the whole system wouldn't have really changed that much. And now we're observing that the star suddenly is not moving away from us anymore, but towards us. Which means the opposite. So instead of red shifted, it's getting blue shifted. So the light is not stretched anymore. Shifted towards the blue end of the spectrum. We have a small temporal variation in radial motion of the host star, and this gives us or reveals to us the exoplanet. It's otherwise invisible to us, but because of the change in the radial velocity, we can suddenly see it indirectly. So again, we have not actually observed the exoplanet, we simply observed that star, and this gave us the hint we needed. This method is the best for finding large exoplanets that are also very close to the host star, because the larger the mass of the planet and the closer it is to the star, the bigger is the influence on the star. And that will mostly be planets that are most likely don't have we don't expect to find life like it is on Earth on such planets. It's mostly hot Jupiters, which are very massive. So hot Jupiters are very close and fast and cause a large stellar wobble. It's also very good for mass estimation, since it relies on the influence of gravity, and it also depends on the inclination again. So we have the sun here, an axis. There is we, the observer here. The planet might rotate to this degree around the sun, around the star. The orbital plane is tilted at some unknown angle to our line of sight. So if the planet rotates around the star like this, then we have an inclination angle which we call I, which is usually called I. And this also influences how much we see of the shift. If we have an phase-on system, we cannot observe the change in radial velocity, because while the star is still shifting position, it's not actually the radial component that is shifting towards us, right? So this is a phase-on view. So we cannot see the spectral change in the velocity. It's just shifting its position, but that's way harder to detect. That's something we could detect in direct observation. In this case, the edge-on view, this is where we could directly observe the shift in position. Mostly we observe a mix of both inclinations. These are like the extremes of the inclination angles. The spectrograph will only detect the movement component towards or away from us. And since only a portion is detected, that means that any measured mass will only be like a lower minimum. Also, we have to take into account that there are stars, very high mass stars, that have a similar effect. These high mass stars have a very turbulent atmosphere where we also have like a light shifting away from us or coming towards us, and then we get the same shift in red and blue, like this temporal variations in the radial motions. So that will be a larger error. Using astrometry makes use again of the movement of stars. The problem with this method is that we need extremely precise measurements. We again look at the shift of the position of a star in the sky due to interactions with a planet. But this time we don't look at the wavelengths of the light. We don't use spectroscopy. We look directly at the change of position. This is extremely difficult to achieve, especially from Earth. The effect is very, very small. We make use of the same effect. Because there's a planet, the star is shifting in position. Missions like the Gaia missions can achieve this level of precision. But from Earth, it's going to be really, really difficult because we have seeing effects, and the effect is just very small, too small. We have to remove the parallax and the stellar proper motion as well. Like when we, as our system, Earth and Sun, moves, then we also have a small shift in position. So we're gonna have to get rid of this as well. And also the star has a proper motion additionally. So we also have to subtract this, and then the residual is what is the influence of the planet. The Gaia mission is able to make measurements like this, since it's measuring a lot of these kind of parameters. It's a space observatory. We see the motion of the star through the galaxy, like its linear path. And then we also see like an oscillation effect. This oscillation effect is due to the Earth's movement around our sun. Like each one of those is 1 year. Now if this star also has a planet, then again we have a small shift in movement, so it will like deviate from this predicted path. And this offset is due to a planet's influence. We can also use direct imaging. Now direct imaging is a direct method. It needs a very high contrast of star and planet. So if a planet is too close to the star is overshadowing the planet and we cannot see it anymore. Planets are tiny, so direct imaging is extremely difficult. So this method actually does not use any indirect parameters. It's just really simply looking at it. Most planets, for a planet to not be overshadowed by the host star, it needs to be further out. Planets close to the host star are not as likely to be detected with this method. And planets with a large distance that is needed to get the kind of contrast we need will probably be outside of the habitable zone again. So we might find an exoplanet this way, but probably not one that has living conditions like on Earth. Also, we have to make sure that the planet is actually bound to the system. That's not something else. Now, if we go to exoplanet.eu, we can see that For the astrometry method, we have 15 planets. If you go to imaging here, we actually have 116 planetary systems. So that's actually quite a bit for direct imaging. But astrometry is even harder to achieve, so we barely have any in Vista's method. Let's look at the last it. The last technique is gravitational microlensing. This of course happens because massive objects warping the space fabric around it. So the light bends in the space curvature, it's getting distorted, and it's changing directions. The gravity of the star and the planet are focusing the light rays towards the observer. If we have light rays of a background star behind another star with a planet, then the light rays are bended around the exoplanet and its host star, making the background star visible to us with an increased brightness. Okay, we look at it first without a planet. We see how this looks, because we don't need, of course, a planet to bend the light. It's just that it's getting bended additionally, and that's revealing the exoplanet. But first we have only the background star, and we have the front star. So the light of the background star gets bended around the front star, and this way it's like increasing. It's functioning as a lens. The light of the background gets enhanced, gets brightened. So we have this bump. We have this bump here of an increased brightness when the gravitational microlensing event is happening, like when the background star moves behind the front star. Now let's look at the same situation with a planet. The background star, the foreground star, but now we also have a planet. We put a planet here. So again, we have flux at the y-axis and time as the x-axis, by the way. Now let's look at the light curve. We have the same bump, increase in brightness again, but now we also have another small bump. And this is indicated in a planet. So if we see a light curve looking like this, we know the star has an exoplanet. It's a second smaller lensing effect. The light of the source, like of the background star, is appearing as an Einstein ring. It gets bended around the space fabric in all these directions. So here, if we have like without a foreground star, it would just go directly to us with a certain brightness. And now if we have a foreground star, we have the foreground star functioning as a lens, increasing the brightness of the light reaching us as it bends around this foreground star in form of a ring. We can also find rogue planets with that, like free planets that are floating around without actually being bound to a host star, since they are also bend the light. So a small lensing effect in this case though. We can also detect planets in systems that are quite far away from us because of this lensing effect, right? We have an increase in brightness, so we can see farther away. But we can only observe this event one time. It's a one-time thing. That's it. If we miss it, that's it. We cannot observe it again. And the observation window for it is also very, very short. For Jupiter-Mars planets, it's days. For Earth-Mars planets, it's even only hours. So it's very easy to miss these kind of events. You would need to constantly monitor stars in real time. There's also like an ideal distance the star has towards the host planet. If the star is too close to the host star, it's just gonna be one blended into the big bump from this host star. Okay, let's summarize. Planets that would be otherwise invisible to us, they're not really invisible, we just can't see them because they're not bright enough. Influence its host star, and therefore, and through this way, make themselves known to us. We can detect these planets by analyzing host star properties. Indirect detection methods are the main source in finding exoplanets. Most exoplanets are found with the transit method or the radial velocity method. There's also a case of observation bias. Planets close to its host star are easier to detect. They also will have more circular orbits. If we have stars that are very low, they are very faint. Their changing properties are harder to see. Or we need better instruments for it to really make out the differences. If we have two high mass stars, they have a very turbulent atmosphere and therefore can contribute to a lot of errors in these kind of measurements. So if we have a graph here, we have low mass on this end and high mass on this end. And here we have the number of stars. We will most likely have a concentration of findings in the middle of these two. There's also the case of if the orbit of a planet is too large, so the planet is too far away from its host star and it takes too long of a time to go around, orbit the host star, then the detection time is just too long for us. Instrument time is valuable. Just observing one object for years, it's not very feasible. So let's look at a very special graph. It's Hugh Osborne. I highly recommend visit his site. It's very informative. He has made this graph where you can see the detection of exoplanets over the time. First you see the solar system planets. They are marked in blue. Now if we increase in time, suddenly all the other detections appear. You can see an increase with the radial velocity method. Now the transit method starts to appear. Every now and then you see microlensing imaging. Astrometry is not even honored. We saw earlier it only has very, very few of those. But you can also see that most of the planets are on the higher end of the mass range. Really, most of them are higher mass than Earth. So the mass on the left are in Earth masses. So the one is the mass of our Earth, and we can see that most of the detections are higher masses than Earth, which is probably an observation bias. That we saw that it's easier to detect higher mass planets. Yeah, I highly recommend going to this website. And that's it for me now. I thank you for watching. Hopefully soon I will make another science stream on Twitch.